All right, guys, let's begin. We have 3 more lectures counting today. Graded homework number 11 is actually up on the D2L. For those of you who haven't seen it yet, we're going to give you another day to get it in. If you want to get it in tomorrow at your recitation, terrific, do it. But if you need to wait till Thursday class, you can hand it in class on Thursday or in Math 108 at the window. We'll take account of papers delivered up to Thursday afternoon. So that's graded homework number 11. The final graded homework number 12 is here on the desk and up there. There's hard copies here. It'll go out on the web or on D2L as well this afternoon. So, I also uploaded many trial finals. How many of you have actually taken a look at the guide for preparing for the final and the questions behind it? Great. I guarantee you, if you can do the questions there, you should do very well in the final. The final consists of 4 questions with many parts, and I'll be going over next Tuesday. I'll be going over in some detail what the expectations I have for you in the final. There's very few in fact there's no trick questions. It is straightforward. It is testing in the sense that it covers most of the material, if not all of the material you have covered in class. But, like I say, a lot of the questions that are likely to appear will be either the same or almost the same as questions you've seen already on your previous exams or on that trial final or on the other trial exams. Question?
Are the tutoring sessions going to be continuing through the finals week?
Yeah. That's a good question. I was just going to come to that. The tutoring sessions, if it's okay with Alex and Caitlin, will continue till Monday, what would that be? The 16th, is it? Yeah, Monday the 16th. Are you game to do it on Monday the 16th? Excellent, okay. So the tutoring sessions, remember they're 10 to 12 on Mondays, Math 241 East, 9 to 10 on Thursdays, 10 o'clock Fridays, and at 1 o'clock Fridays, again in Math East 241. Yes?
Do you want me to do it on Dead Day? Next Thursday?
Dead Day. Is Dead Day Thursday?
Yeah. I don't mind. I didn't know.
I mean, unless, I won't get excommunicated or anything like that, will I? I mean, if I do something on Dead Day, it sounds very ominous. But I would like if you would do it on Dead Day, and I'm sure your colleagues here would like it too. I will be available again 7:15 tomorrow morning, at 8 o'clock on Thursday morning, also the following week in those times, also Dead Day, I will turn up. If Brittany is going to turn up, I'll turn up on Dead Day. And then the day before the final, which is the 17th, the final is the 18th, the 17th, on Tuesday the 17th, I have booked Math 501 for 2 hours from 10 to 12. So if there's any questions at that stage, I'll be there to give you any help I can. Are there any other questions now about the... Yes?
Yes, could you clarify exactly how the exam redo homework points count? I'm a little confused about that. Like, how does that factor into the test?
The exam, which exam, the final or the previous one?
The one we just took.
The one you just took, the first exam, actually I marked the exam out of 180 and you got an extra 20 for the take-home bit. This second exam, number 2, you got a full 200 for the exam taken in class, and you get 40 towards your graded homework for the retake. So the total score for graded homework will be a total of 150 when we finish. The quizzes will be either 150, or if they're less than 150, as a bonus, everybody will get the extra up to the 150. Okay, so what are we going to do now? We're studying classes of equations which have 2 dependent variables, and they're autonomous equations, meaning that the independent variable t does not appear in either f or g, the right-hand sides of the equation for x and y. Now, the equilibrium points, or fixed points sometimes they're called, are those points, xe, ye, such that they make both f and g 0. Now, we look for solutions of these equations. X as a function of time, y as a function of time, but very often it's more revealing, you gain more understanding of the phenomenon you're trying to study by drawing the trajectories x of t, y of t in the xy phase plane. So in other words, imagine you've solved x as a function of t, y as a function of t, and at each time t, in your allotted interval of time, you plot where x of t, y of t lands, and then those trajectories will be curves in the xy plane, and those curves I've shown you will be solutions of the equation gotten essentially by dividing the 2 other equations. It's not really dividing, you have to use the chain rule. But dy by dx is g over f. Notice, if we allow infinity to be an okay number, because it means the slope in the yx plane, the slope is vertical, so we'll allow infinity, then the only places where the derivative, dy by dx, is not defined are those places where both f and g are both 0. Then it's indeterminate. So everywhere in the xy plane, except the equilibrium or fixed points, you have a definite slope. Now, at the fixed points, as we find out and we've seen already, you can actually have 2 curves going through the fixed points. And we're going to see that in our first example today. Now, if we can solve dy by dx as g over f, then in some sense we have the solution curves which we can then draw in the xy plane. However, more often than not, it's not possible to solve dy by dx as g over f analytically. We will be doing an example now in a minute where we can do it in one case analytically, and then when we include friction, we can't. So the question is, what do we do then? What do we do if we can't solve dy by dx equals g over f analytically and then draw these curves? Well, that's the main focus of today's lecture and next day's lecture. So the example we're going to do is the following. F is going to be just y, and g is going to be a little friction, and then we're going to have a potential. It's like a flow on a surface which looks like this. This is minus, if we think of this as minus dv by dx, v is the shape of our hill. Okay? So if this is minus dv by dx, the v of x is going to be minus x squared over 2 plus x to the cubed over 3. I'm going to take v of 0 to be 0. So that looks like what? Well, if I draw the curve, this is the curve z equals v of x. It'll come like this, then down and up like this. So this is x, this is z, and this is the curve z is v of x. You see, it looks like an upside down parabola, minus x squared over 2 for x near 0. But then for positive x, it takes off as x cubed over 3. So we have a puck, a little ball, sliding in this ice sheet. And x actually is the distance measured along the curve, starting from this point, which is x equals 0. And the derivative of x, dx by dt, is y. Y plays the role of the velocity along the curve that I've just shown. So this autonomous system describes the motion of all the different possible motions that we can have on such a surface. Now, in general, because if b is not 0, we can't solve the equation dy by dx is g over f. Question? Why? That's a convention. We just that we write it as the negative of some shape. We could write it as the positive if we like, but it's just the convention that's used for potentials. Okay. All right. So we're sliding then in this surface. Now you can sort of see what to expect. We'll have, if we had no friction, there'll be some motions which will just slide backwards and forwards in this well. There'll be some motions which try to climb the hill and maybe make it and maybe don't, come up and back. Some will get over the hill and maybe go on up here. And then, of course, they'll have to slide back out. Let's see if we can see all these various possibilities. So, first case, case 1, we'll take b, the friction, to be 0. Now, I have dy by dx is x minus x squared over y. Now, this is separable. So, all the y's together, all the x's together, and I find that y dy minus x squared dx equals 0. Integrating, I have half of y squared, then minus x squared over 2 plus x cubed over 3 equals constant. So we can interpret this, imagining the mass of the puck to be just 1. This is the kinetic energy, and this is the potential energy. This is the potential. So that's why we use the minus, the convention, so that we get kinetic plus potential is constant. Total energy conserved. Okay. So now for various e's, this is a set of curves in the xy plane. So here is the xy plane. Let us look at these different curves. The simplest curve. Let's look at the curve that goes through the origin. Oh, first of all, let's write down what are the fixed points here. What are the equilibrium points? Right, 0, 0, and 1, 0. In other words, this is 0, y has to be 0. So this y has to be 0 in both cases. If y is 0, then we can have x equals 0 or x equal 1. They correspond to the two positions, as you can imagine, here and here. Now, what do you imagine happened? This guy is what? He'll be Lyapunov stable, especially if there's no friction. He'll be asymptotically stable if there's positive friction. Right? Because if I give the guy a nudge down here, he'll just oscillate backwards and forwards in the neighborhood. Starts near, stays near. This guy, on the other hand, we expect, once you give him a nudge, he's gone, down one side or the other. So he is unstable. Now, we're going to kind of learn about the nature of the unstable and stable points. Let's look at the curve through 0, 0. Through 0, 0, what's the value of E? 0. Okay, so the curve with E equals 0 is a half y squared minus a half x squared plus x cubed over 3. Okay, now what does that look like very close to the origin? So if x and y are both small, then the dominant terms are the y squared and the x squared. This guy is smaller. So near the origin, it looks like y squared equals x squared. That's a pair of straight lines. So it looks like y equals plus x and y equals minus x. So they, in fact, are the tangents. They are the tangents to the actual curve. So this is y equals x. This is y equals minus x. So now what does the rest of the E equals 0 curve look like? Well, you can see it'll be y squared is x squared minus 2/3 x cubed. So for each x, we'll have 2 y's in most places, not all places. And in fact, what you're going to find is the curve is going to look like this. And then this goes off to infinity like that, and that goes off down like that. And the 1 position, the 1 is just in here. That's 1, and that's the 0. Now you can use your JODE, and we look at the various kinds of orbits. Orbit number 1 for B equals 0 will be just the orbit that goes around like this. Now, which direction as time increases? If y is positive, because dx by dt is y, if y is positive, dx by dt is positive, as t increases, x increases. So this is the direction of the motion. Then down here, it's in the opposite direction. So for this trajectory, in the xy plane, the curve just goes round and round, almost like a circle. Right? So, what is the value of E if, supposing I take it very close to the point 1, 0? What is the value of E here? By the way, we've already decided this is E equals 0. How about that little circle that is right here? First of all, what do these correspond to? These correspond to just motions slide back and forward, back and forward, and so on. Now, if we just give it a little nudge, it's back and forward, back and forward. That's this circle here. What's the value of E right down here? What's the value of E at x equals 1, y equals 0? What's the value at x equals 1, y equals 0? Minus a sixth, right? So this is E equals minus a sixth. Okay? So between E equals minus a sixth and 0, you get curves in here. But you also get curves out here. Okay? There's a curve here, and there's a curve here, like this. This is the minus a half. This is x is minus a half. So this also corresponds to E equals minus a sixth. So this is E equals minus a sixth. So the curves for E between minus a sixth and 0 are curves that go like this down here with this final one here, or curves in here. Both have the same energy. Now, why is that? What's the connection? Well, what you're doing here is the motion here. Imagine, take the motion here, just at the bottom where E is minus a sixth. But imagine the other motion, that I give the thing a puck here, it goes up and just gets to the bottom of this well here, and then descends back down like that. That's a curve. We start with positive in the negative x region, but with a positive velocity. So y is positive, x is negative. E is roughly minus a sixth. Okay? So I flow up the hill, but then I can't get beyond here. I don't have enough energy. It stops at this point and then is going to turn around and come back down here. So these are the direction of the arrows. This guy has the same energy as the guy just going backwards and forwards in the well. Because roughly the energy of this guy, because he isn't moving very much, his kinetic energy is almost 0, so it's just his potential energy, which is this distance here. Yes?
Just from my own curiosity, where's gravity expressed in the equation here?
Yeah, gravity we've taken to be 1. If you remember, I gave you a handout deriving the equation for, in fact, it was in the hill where the potential was minus x squared over 2 plus x to the 4th over 4. And I derived the equation there. So you have the m and the g in this equation, and what we've done is we have rescaled variables so that the g effectively is 1. But you're quite right to ask. So if you go back and look at that handout, I forget exactly what it's I think supplement or something to the derivation of these equations. So you see, this guy, when he gets up to here, his y is 0, and his potential energy at this point is the same as the potential energy at this point. So you see, in between minus a sixth and 0, this is E equals minus a sixth and 0, there are actually 3 possible routes. See, this route, and this route. There's 3 possible routes for a given x. Then once you go beyond up here, once you go to energies up here, now E is positive. Now what do they correspond to? Well, if I give the thing, supposing I start the thing here. So I start the thing with 0 velocity at that particular x. Well, that's like starting at 0 velocity you're starting out here. So what's the curve going to do? Well, you know, this is just going to roll down the hill, up and over, and keep on a-going. Right? Because there's no friction. So if he's high enough, if he's above this point, he just rolls down and over this point and head on down there. And so what he'll look like is this. And you follow that. So this is this motion from here. On the other hand, if you gave it a good hit up the hill here, like this, and if you give it enough hit, it'll go up, then turn round, come down, run right out again. And that'll be something like this. Right. So these are the various kinds of motions. For E less than minus a sixth, the thing doesn't get up to this height, it just gets up to, say, here, and then comes back. So these are these curves here. Okay, so this phase plane now tells you about the nature of the system. And these guys, if you remember, we call them separatrices because they separate. So the E equals 0 curve separates the different kinds of motions that we have. Now, I also introduced the notion of stable and unstable manifold. Of an unstable, this is a saddle point. Okay? I'll tell you in a minute why we call this term a point a saddle point. But you can see, in what are the arrows here? Because y is greater than 0, dx by dt is greater than 0, so the arrow goes this way. X increases as t increases. Down here, it decreases. Here, it increases as t increases. And here, it goes this way. So it's like, this is like a saddle. Because if I start on these lines or on these curves here, okay, and I allow time evolve, I'll end up back here. On the other hand, if I start on this one, I go away. So imagine a saddle, okay, in one direction it looks like this, and then in the other direction it looks like that. Okay? So in one particular direction it'll come back to the center, but in all other, if you move it slightly off this curve at all, then of course it goes away from this point. Does everybody see that? If you start anywhere near this point, except on this very special line, this very special curve here called the stable manifold, you will go away from the equilibrium point, which here is 0, 0. And the nature of the structure of the behavior in this neighborhood is divided by this stable and unstable manifolds. Let me put up the definition now. The stable manifold, and we'll run it jointly with the unstable manifold, means here a curve, of the unstable saddle (0, 0) is the set of initial conditions x0, y0 through which the trajectory tends to 0, 0 as t goes to either plus infinity or minus infinity. So the stable manifold is the set of all starting points such that if you start on them, and you allow time flow, you'll end up exactly back here. The unstable manifold is if you start on this manifold and you let time flow backwards to minus infinity, then you'll end up at this point here. Now, just because starting with these special values here on the stable manifold, you end up at 0, 0, doesn't mean that this is a stable point. It's not. To be stable, I must be able to start anywhere in his neighborhood and stay in his neighborhood. And clearly, that won't happen. Clearly, if I give this guy a little puck, it will go away from the point. The stable manifold corresponds to if I start the thing here and I give it just enough velocity to, as time goes to infinity, just to crawl up and just stop at the top. That's the stable manifold, but you can see it's impossible to give that thing that exactly the right velocity to achieve that. Impossible. Because any little error and it'll either go over the top or slide back. And that means any little error, you're not quite on the stable manifold, you come almost all the way in, but then you shoot off in the direction of the unstable manifold. Question?
So is there an overlap between the stable manifold and the unstable manifold?
This very interesting question. The gentleman asked, is there an overlap? And actually, there is. They're the same. In the sense that if I follow the unstable manifold out here, he becomes the stable manifold of 0, 0 at the end of that circuit. Okay, so now what's that? What's that particular circuit? The circuit corresponding to this trajectory. It's I start here at 0, I give the thing the tiniest of touches this direction. It'll go down, up, it'll just get to about here, and then it'll come all the way back and roll up. It'll take an infinite amount of time to do this, right? But that's the trajectory it will take. So it's both this trajectory, if you consider the whole thing, is both the unstable and stable manifold of this. This is called, actually, it's given a name in dynamical systems theory. It's called a homoclinic orbit. It's an orbit that joins itself to itself, at a fixed point, back to its fixed point. Going away on the unstable manifold, coming back on the stable manifold. Yes, question.
If our graph were reversed, would the stable manifold continue to go to negative? Like
Right. So Caitlin's question is, supposing the thing was over here, so I make it minus x squared over 2 minus x cubed over 3, then in that case, no, it would still be, they'd still have these arrows, because still dx per dt, you know, y is positive, dx per dt would be positive up here, so the arrow is always increasing x on top and decreasing x below. Yes?
So with the point to the right, that everything's circling around, would that be a stable?
This here?
No.
This one? Yes, that's a stable, and if there's no friction, it's called a stable center. The thing just oscillates backwards and forwards in the well, right? So now the question is, could we kind of get an idea of what the picture would look like when B is not 0? Okay, so what happens we haven't quite trained that chemist, but almost. He's done very well. So, what happens if B is not 0 but positive? Now, the equation would become, A2 would become dy by dx equals minus by plus x minus x squared over y. Now I can't solve that equation analytically, and I doubt if anybody really can. We can do it numerically, of course, and if you use JODE with b, say, equal 0.2, you know, you'll see the result there. In fact, this is precisely, as you've seen, what we're doing is your graded homework number 12. What we're doing now today is just graded homework number 12. So, what are we going to do? Well, in some sense, you see, from this picture, we sort of learned that in some sense, everything, if we know roughly what goes on in this neighborhood, the neighborhood of the equilibrium 0, 0, and this neighborhood here, we can sort of get a fair idea of what the trajectories will do. So, let's do that. Let's take a local analysis. A local analysis near each of the fixed points. 0, 0, and 1, 0. Right. So I'm going to work near 0, 0 first. So I'm going to let x equal 0 plus capital X. Y equals 0 plus capital Y. And I'm going to treat capital X and capital Y as small. So now the equations become dx by dt is y, and dy by dt is minus by plus x, big X, minus minus big X squared. It's the same equation because I just replaced x by big X and little y by big Y. But now, this time, we're going to take these as small. These guys are small perturbations. So I'm going to neglect this guy compared to the big X. Because if big X is 0.1, x squared is 0.01, and it's much smaller than 0.1. So we can analyze, in fact, what I'm going to tell you now is that the behavior of this linear system, which is an approximation to the proper system, tells us exactly what goes on in these neighborhoods, even for the nonlinear system. So, but now, this guy is easy to solve. It's linear. Replace y by dx by dt. Then the second equation becomes d2x by dt squared, plus b times y, which is dx by dt, and then minus capital X equals 0. Hey, we're back to halfway through the second part of the course. Homogeneous, linear, constant coefficient equations. This is easy to solve. Let's solve it. We let x equal e to the RT. We get r squared plus br minus 1 equals 0. The two roots are r. 1 and 2 is minus b over 2 plus or minus the square root of 1 plus b squared over 4. So the roots of r squared plus br minus 1 are just this. But look, one root, r1 is the top root, it's positive. So note, r1 is positive, r2 is negative. So now what does big X look like? And big Y? Okay? So, big X is a e to the r1t plus b e to the r2t. Right? It's a linear combination of the two solutions, e to the r1t, e to the r2t. Remember, r1 is positive, r2 is negative. What's the y? The y is the derivative of this. r1a e to the r1t plus r2b e to the r2t. So I'm going to write this, I'm going to put back, this is x minus 0, y minus 0, because big X is 0 plus, little x is 0 plus big X, little y is 0 plus big Y. This is equal to a e to the r1t times 1 r1 plus b e to the r2t 1 r2. Where r1 is minus b over 2 plus the square root of 1 plus b squared over 4. This tends, if b goes to 0, this just tends to 1. r2 is minus b over 2 minus this, 1 plus b squared over 4. And as b tends to 0, this tends just to minus 1. So now look, what choice do I have to make for A to make sure I'm on the stable manifold? In other words, I want to choose initial conditions, namely, I want to make choices for big A and big B, so that as time goes to plus infinity, the solution, this will decay, the solution will decay to 0, 0. So x will go back to 0, y will go back to 0. Now, that will happen with the R2, because he's negative. So what do I have to choose? I have to choose big A to be 0. So I have to choose my initial conditions, so the big A turns out to be 0. And that will be the stable manifold. So let's go back up here. So the stable manifold occurs for initial conditions where big A is 0. Then, what? If this is 0, then y is just r2 times x. Right? Because x is b e to the r2t, y is b e to the r2t times r2. So then y is equal to r2 times x. And this is equal to, in our case, minus b over 2 plus square root of 1 plus b squared, minus over 4, okay, times x. And as b tends to 0, this just tends to minus 1. Y is minus x. So the nature here, the unstable manifold is changed a bit in slope. Imagine if b is very small, there's tiny change in the slope of the stable manifold, but not much. How about the unstable manifold? Occurs for initial conditions where b is 0. Because when b is 0, and I run time backwards, because r1 is positive, x and y again tend back to 0, 0. Now, in this case, y is r1x. And this tends to plus x as b tends to 0. So, notice these saddle points, these are always unstable. It doesn't matter what b is. There's no way you can choose a friction to make this a stable point. As you can see, I mean, the friction will slow it down, okay, but it won't stop it. So, what we found, what this theory, linearizing about this point, has found is the tangents here to the real stable and unstable manifolds here. So it's given us these directions. Now, we've taken care of, we know what's happening here. Now, the stable and unstable manifold, the topology doesn't change. The directions change slightly with B. If you made B like 0.1, okay, it would be Y is probably minus X, but it would be 0.95X. Whereas the unstable manifold would be Y equals plus 1.05X, something like that. But it's really the very same topology in the neighborhood of the unstable saddle. Now, what happens near the other point? So now we're going to do the local analysis near 1, 0. Okay, any questions on this before we go on? It's very easy. We just linearize the equations about the equilibrium point. Then we have linear constant coefficient equations, which we're very good at solving, and we get their solution. We'll do the same again now around 1, 0. In this time, this time, I'm going to let x equal 1 plus x, y equals 0 plus y. Yes?
The last example, the solution to the local analysis near 0, 0
Right.
would be y tends to negative x for the stable manifold.
That's, yes.
So that would be what you would want us to write down.
Sorry?
That would be the answer that you would like require from us. Would be
Yes, if I, yes. In fact, that was, yes, I think I asked you, graded homework number 12. Okay, in this case, actually, you're in a slightly different potential. So in this case, it would be the same, actually. Y equals plus or minus x. Yeah. Yeah. All right. So now, we have to replace this by 1 plus x, and then minus 1 plus x all squared. So this, when I expand this out, it's minus 1 minus 2x minus x squared. The 1's cancel. The x and the minus 2x add to minus x. And then I have a minus x squared. So this whole thing becomes minus x plus, minus x squared. Now again, we're taking x and y small, big X and big Y small. We forget that with respect to the x. Now again, we do the very same thing. We replace y as dx by dt. Now I get the equation d2x by dt squared plus b dx by dt. And now it's going to be plus x equals 0. Okay? So the only difference in looking around the 0, 0 on stable point and the 1, 0 is that the sign, instead of this being minus capital X, this is now plus capital X. But that makes all the difference. Why? Because now let's look for solutions x equal e to the RT. Now I find r squared plus br plus 1 equals 0. R equals minus b over 2 plus a minus b squared over 4 minus 1 if b squared is greater than 4, or it's minus b over 2 plus a minus I square root of 1 minus b squared over 4 if b squared is less than 4. Right, now what are the two solutions? What are the solutions going to look like? Let's take the top case first, where b squared, the damping is quite strong. Okay, so b squared greater than 4 case. Then my two solutions are x is a e to the r1t plus b e to the r2t, where r1 is minus b over 2 plus the square root of b squared over 4 minus 1, and r2 is minus b over 2 minus the square root of b squared over 4 minus 1. Both are negative. Both are negative if b is positive. Then the corresponding y is r1 a e to the r1t plus b r2 e to the r2t. And I'll write this as x minus 1 y equals a times e to the r1t, 1 r1, plus b e to the r2t, 1 r2, where both r1 and r2 are negative, or either they're positive if b was negative. But let's take the friction to be positive for the moment. So now what happens x minus 1 and y as time goes on? What's the sign of R1 and R2? What are the signs of R1 and R2? Negative, aren't they? So what's going to happen to x minus 1 and y as time increases? They decay. Okay? And you can see from here, who is the biggest negative number? This guy. R2 is more negative than R1. So after a long time, which of these two terms is going to dominate? R2 is the bigger one. So it'll decay, what? Quicker. So after a long time, it's this guy will dominate. So you will come into this point, x equal 1, y equals 0, along a certain direction. Okay, so you have this, you'll come in, it'll be along a certain direction. And you come in this way here, okay? You come into 1, 0, like this. All the solutions will come in along this direction. And this will be the direction y equals r1 times x minus 1. This was like when in the mixing problem, we saw from JODE, all the solutions come in along the weaker decaying direction. This is called a stable node. This is called a stable node. N-O-D-E. If B was negative, then both R1 and R2 would be positive. And then you would have an unstable node, and all the points would leave here. Okay? Now, so that corresponds to an orbit here. We have damping. We start here, and the friction is so much that the thing just slides directly down the hill and stops. It doesn't even oscillate once. It just goes directly down the hill. No backwards and forward stuff. Just goes directly down the hill and stops. Okay? Now, if b squared is less than 4, so now let's look at this case. Less than 4. Now, R1 is this plus I times 1 minus b squared over 4, and minus I times 1 minus b squared over 4. Okay? Now, the real parts, of course, are both negative if b is positive, and vice versa, positive. So now what's going to happen? Now, x equals a e to the minus b over 2t cosine square root of 1 minus b squared over 4t plus b times e to the minus b over 2t sine of this. And then you can compute the y as well. Just it's the derivative. Okay? Yes, you can do it. You can. Now, what happens in this case? Now you spiral in. Now what will happen is, instead of it coming directly in, dive bombing in, now it's going to roll forward, backward, forward, back, da, 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 all the way, finally coming into the center. So it will look something like this. If you start, say, here, it'll just wind its way, spiral its way in like that. So this will be a stable spiral. A stable spiral. And if B was negative, if you had negative damping, if you were in an amplifier situation, then you'd have an unstable spiral. Things would spiral out. Okay? So, the complete nature of the fixed point, its stability properties, is governed simply by doing the linear problem. Now, what's the full picture going to look like? What's the full picture going to look like? Let me draw it for you. Let's first of all actually think about it. Supposing I have some positive friction. There are two things that can happen. If I start up here, okay, if I start high enough up here, the friction won't be enough to stop it getting over here, and once it gets over here, it'll go all the way to minus infinity. But I could start, say, here, and if there was no friction, of course it would get over this hill, but with the friction, it may just not quite get over this hill and then oscillate backwards and forwards. So the xy plane, and this is where you use the actual numerics, the JODE. The JODE, it'll look something like this. Here's your 0.10. Now I'm going to talk about the case where b squared is less than 4, so things spiral in. So you have this unstable manifold coming out like this, and it'll spiral in like this, to this point, like that. Then you'll have a stable manifold coming in something like this, and also out this side. And this side. Well, no, this will actually maybe come over the top and come in. The dividing line, the set of initial conditions which eventually end up at 1, 0, are called the basin of attraction. That set is called the basin of attraction. And you can see it's not everything. So if you start high enough up here, this will have enough lick to get over the top here and end up at minus infinity. So it's going to end up going out here and down like that. Now the question is, what's the boundaries? What's the boundaries of this, the basin of attraction? Now I'm going to leave this to you to play with. I would like you to use JODE and try and figure out in the xy plane what set of initial conditions will end up at our asymptotically stable spiral point here. And I'm going to give you a hint. It'll have a lot to do with the stable manifolds of this unstable saddle. That they will decide which parts belong to the basin of attraction and which sets of initial conditions have you ending up going down here. Okay, I'll show you the picture next day, but I'd like you to explore this first. Take B equals, say, 0.1 or 0.2. Okay, and look at JODE. Right. So now we see that by analyzing the behavior of the equations in the neighborhood of the equilibrium points, we can more or less begin to sketch out the nature of the trajectories in the phase plane. In the final few minutes, I'm just going to start for you sketching what you do if we're not dealing with a particular example, but we're dealing with an F and G in general. Okay, now this is on pages, starting pages, I believe 20 in the lecture notes 22 through 33. Lectures 22 through 30. There's 33 pages. They've been updated so that the numbers are correct, so you might want to get the updated version. But now I'm going to show you what's on, essentially, page 20 of those notes. I'll sketch this for you now. The TAs are going to do this again after your quiz tomorrow, and I'm going to do it again on Thursday, because you need to see these things several times. Now we're going to deal with dx by dt is f of x and y. dy by dt is g of x and y. And we're going to look in the neighborhood of the equilibria. So we're going to let x equal little xe plus capital X, y equals little ye plus capital Y. Now I'll substitute into these equations. Since these are constants, I just get dx by dt equals f of xe plus capital X, ye plus capital Y, and dy by dt is g of xe plus capital X, ye plus capital Y. Now, one of your favorite parts of Calculus 129 was doing Taylor series. Now, you did Taylor series in one variable. And in one variable, this would be, forget this would be f at xe plus capital X, the derivative of f with respect to xe, at the point xe, plus 1 over fact 2, capital X squared, and so on. But we are only going to keep up to linear terms, so it's very easy. So this will turn out to be f of xe and ye plus the partial of f with respect to x at xe, ye times big X plus, if you have two variables, it's the partial of f with respect to y at xe, ye times y, plus terms with x squared, xy, y squared, which we are going to ignore. So this is just Taylor series for a function of two variables, just to leading order. The g will be, of course, the very same, except with f changed into g, plus dg by dy at xe, ye times y, plus x squared, xy, y squared. Now, what is the value of that guy? If I estimate f at the equilibrium point xe and ye, what's his value? 0. Boom, gone. What is g at xe, ye? 0. Bang. Now I'm going to call this guy A, I'll call this guy B, I'll call this guy C, and I'll call this guy D. Therefore I end up with two very simple equations. dx by dt equals ax plus by. dy by dt is cx plus dy. Two linear constant coefficient equations. We can get rid of the y here from this equation in terms of x and dx by dt, shove it in here, and get a single equation, second order, for x. And you get d2x by dt squared minus a plus d times dx by dt plus ad minus bc times x equals 0. But these are constants. We'll call this p and this q. And boys, you know how to solve that equation because you've done it dozens of times before. So starting next day, we will start from this position and go on to characterize and categorize the nature of all the equilibrium points, their stability natures. Before you go, one more comment. Very important. Very important. Notice, if I got an equation for y instead of x, would I get a different equation? The answer is no. The equation for y will be the same as the equation for x, exactly. The equation for any linear combination of x and y, hey, guys, stop the squeaking. The equation for any combination of x and y will still be the same. Now, for those guys who are doing a bit of linear algebra, the reason the equation is invariant to any transformation of coordinates appears in essentially the nature of the coefficients. This guy is the trace of the matrix A, B, C, D. And this guy is what of the matrix A, B, C, D? The determinant. And under transformation, the trace and the determinant are invariant. Okay? So that's just for the people interested in linear algebra. See you Thursday. See you tomorrow.